Where did all the antimatter go? I mean, it sounds like a riddle, but for physicists, this is maybe the universe's biggest mystery.
It really is. Physics tells us that right at the Big Bang, matter and antimatter should have been created in perfectly equal amounts.
And if they were equal, they should have just wiped each other out instantly, right?
Yeah.
Leaving nothing behind but a flash of light.
Exactly. And if that happened, we wouldn't be here. Your phone wouldn't exist. The sun wouldn't exist. This deep dive certainly wouldn't exist. The universe we see is just overwhelmingly matter. We call it the baryon asymmetry.
And that's a massive contradiction. Here's the kicker. The standard model of particle physics, our best rule book for how everything works, it has a way to explain this, but it's famously weak. Oh, it's way too weak. By about a factor of 1 billion, the math just doesn't add up to the universe we actually live in.
So that gap, that huge chasm between the theory and reality, means we need new physics. We need to find some hidden rule, some undiscovered asymmetry that let matter win.
And that's what we're here to talk about. Welcome to the Deep Dive Lab. Today, our mission is to dive into a breakthrough paper in the journal Nature from a huge international team, including Emma Thanasakis, Kaklamanakis, MAU, and many others. They think they've found the ultimate quantum detective for this job.
And it's a very strange detective, a highly radioactive molecule called actinium monofluoride, or for short, $27 in Text Daily.
Okay, so before we get into the weeds, let's just translate some of that. We're looking for something called CP violation. What fundamentally is that?
Right. So CP stands for charge parity symmetry. The easiest way to think about it is like a quantum mirror.
Quantum mirror, I like that.
The C means you swap a particle for its antiparticle, its charge opposite. The P means you look at its reflection in a mirror. CP symmetry says the laws of physics should be identical in that reflection.
So a perfect mirror, what you see is what you get, just flipped.
Exactly. But for matter to have survived, that quantum mirror must have been slightly cracked in the early universe. The reflection of the antimatter particle had to be subtly different from the original.
That subtle difference, that's the CP violation we're hunting for.
That's the smoking gun. It's what allowed matter to win.
Okay, so that brings us to the molecule, Texerivo. Why use these heavy exotic molecules to look for this tiny crack in the mirror?
Because they're the ultimate magnifying glass. When you bind a really heavy nucleus like actinium to a light one like fluorine, the molecule generates an enormous internal electric field.
How enormous are we talking?
Billions of volts per centimeter acting right on the nucleus. It takes any tiny hint of CP violation inside that nucleus and just amplifies it massively, making it something our instruments can actually detect.
But it's not just any heavy element. The choice of actinium itself is really specific, isn't it? It's about the shape.
It is. This is where it gets really cool. Most atomic nuclei are, spheres or maybe slightly squashed footballs. The nucleus of actinium-227 is different.
How so?
It has what's called an octuple deformation. It's shaped like a pear.
A pear shape. Okay, that's much easier to picture than octuple deformation.
Huh.
Why does a lopsided pear-shaped nucleus help?
Because that asymmetry, that lack of a perfect mirror image in the nucleus itself, makes it intrinsically sensitive to these CP violating effects we're looking for. The target we're measuring is called the nuclear shift moment, and the pear shape enhances its effect dramatically.
So it's like a double whammy of sensitivity.
The double whammy. You get amplification from the molecule's electric field, and you get a second layer of amplification from the nucleus's pear shape.
And this specific isotope, actinium-227, it has a half-life of almost 22 years, so it sticks around long enough to actually be measured properly.
That's the key. It's this perfect storm of high sensitivity and practical usability. It makes actinium monofluoride, arguably the single best candidate molecule for this search.
Okay, so let's get into segment 1. Building this thing. You obviously can't just order radioactive pear-shaped molecules online. How on earth do you make it?
Well, that's the first huge challenge. Actinium is intensely radioactive. I mean, trying to handle even a tiny visible sample in a normal lab would be incredibly dangerous.
Right. It's like trying to build a tiny, delicate ship in a bottle, but the bottle is red hot and dissolving.
A great analogy. So the team had to go to a place built for this.
Right.
The CERN-ISOLDE facility. It's a radioactive ion beam factory, basically, designed to produce and handle these exotic particles safely.
So walk us through the recipe. How do you cook up Texa's CERN?
It starts with a target made of uranium carbide. They blast this target with high-energy protons from CERN's proton synchrotron booster.
And that blast, It just shatters the uranium
It
atoms.
does. It causes fission and fragmentation, creating all sorts of new particles inside the target, including the actinium nuclides we want.
But I've heard actinium is really sticky. It doesn't like to come out once it's made. How do you extract it?
This is the really clever chemistry. First, they heat the whole target to over 1,300 degrees Celsius. It's basically a furnace. Then they pump in a gas carbon tetrafluoride.
And the fluorine in the gas just grabs the actinium.
It does. It forms actinium monofluoride at text AC, which is much more volatile. It turns into a gas more easily. It's like using a chemical hook to pull the actinium right out of the furnace.
That is brilliant. But now you have this hot radioactive gas. You still have to turn it into a usable, focused beam of ions for the experiment.
And this is our first big wow moment from the paper. They used a specialized ion source to create the beam, and the result was astonishing.
What did they get?
They managed to produce a pure beam of these textates at a rate between 6 million and 20 million ions per second.
Wait, 20 million radioactive molecules per second. Why is that specific number so important?
Because sensitivity in these experiments is all about statistics. It's about how many times you can run the measurement. If you only get a few molecules a day, an experiment could take centuries.
But with millions per second.
You can get an answer in a reasonable time. It proves the experiment is actually feasible. It's the difference between trying to solve a crime with one blurry photo versus millions of frames of high-definition video.
Okay, a critical step.
Yeah.
But the molecules in that beam are still hot and chaotic, right?
They are. So the final step in production is to send them into what's called a linear Paul trap. They use helium gas in there to cool the molecules down, slow them, and collect them into these neat, tidy little packets.
And those packets are now ready for interrogation. Which brings us to segment 2, finding the quantum readout switch.
Exactly. So we have our detective, text 8 tau. Now we need a way to read its notes to see what it's found.
How do you do that?
The technique is called collinear resonance ionization spectroscopy, or CRE-IS. The goal is simple, though. Find the exact frequency of laser light that this molecule will absorb.
You're looking for its resonant frequency, the one note that it responds to.
That's it. That specific frequency, that specific color of light becomes our readout switch. We can use it to check the state of the molecule during the final experiment.
So they're just pointing lasers at these packets of molecules and tuning the color until they see a signal.
Essentially, yes. They were sweeping across the ultraviolet spectrum, looking for the strongest electronic transition from the molecule's ground state, which is the stable state you need for these precision measurements.
And what did they find?
What's amazing is they only found one single clear resonance in the whole wide range they scanned. They identified it as the predicted strongest transition, the 8 pi left arrow x1 sigma plus dollar state.
And where was this quantum key located on the spectrum?
Right around 387 nanometers deep in the ultraviolet. And this is huge because it perfectly confirms the ab initio calculations, the predictions made from pure theory by people like L.V. Skripnikov and his team.
So the theorists drew a map and said X marks the spot, and the experimentalists at CERN dug right there and found the treasure.
It's a perfect marriage of theory and experiment, and it's crucial. Without knowing that 387 nanometer switch, they could never build the laser system needed for the actual search for CP violation. This result proves the entire approach is sound.
So we have the world's most sensitive detector, and we know how to read it. Now, segment 3, the astronomical impact. Just how much better is text 8 than what we've had before?
This is where we get to the payoff. The incredible sensitivity comes from two pieces of the puzzle coming together. First, the nucleus itself.
The pear-shaped.
Right. The nuclear density functional theory calculations show that the intrinsic shift moment of the actinium-227 nucleus is 37.1. Now, that number is abstract, but the comparison isn't.
How does it compare?
It's 40% higher than what's found in radium-225, another nucleus that's a major focus of other big experiments. So right out of the gate, the nucleus itself gives you a 40% stronger signal.
A huge advantage. And then the molecule amplifies that even more.
Massively. The relativistic calculations of the molecule's structure show it has an enormous molecular sensitivity factor. When you multiply the two together, text just pulls way ahead of the competition.
So let's get to the bottom line.
Right.
What is this bias in the hunt for missing antimatter?
This is the core takeaway, what the paper calls the 3 orders of magnitude leap. The team, including researchers C. Zulk, K. Gall, and R. Berger, ran a global analysis of what they call the CT-violating hyperspace.
Hyperspace. That sounds a little like science fiction. What does it mean?
It's not fiction, it's just a way to visualize the problem.
Mm.
Imagine a giant, seven-dimensional map that represents every single possible way new physics could be hiding this CP violation. It's a vast, unexplored territory.
And with our current tools, we've only been able to search tiny corners of that map.
Tiny corners! But here's the amazing part. When you factor in the potential data from an anti-stick experiment, and not even a perfect one, just a realistic one they could run for about 100 days, the effect is revolutionary.
How revolutionary? Give me the number.
An experiment like that would shrink the possible volume of that 7D hyperspace by a factor of 6,000.
6,000.
6,000 times smaller.
Wow. That's not just a small step, that's a giant leap. That is the 3 orders of magnitude you were talking about.
It's transformative. It's like you're searching for one specific person somewhere on the entire planet. Previous experiments narrowed the search down to, say, the continent of North America. This one experiment narrows it down to a single city. You're dramatically closer to finding the answer.
And the paper says it's especially sensitive to something called the QCD theta phase, which is related to the strong nuclear force.
That's right, which is a notoriously difficult place to look. So this isn't just a general improvement, it's a precision tool that lets us probe the very heart of the strong force for new physics. It's just a beautiful example of how nuclear physics and quantum chemistry are coming together to answer the biggest question in all of cosmology.
Okay, this has been an incredible deep dive. Let's wrap it up for everyone listening. What are the 3 key takeaways from this breakthrough?
First, I'd say it's the production breakthrough. The team proved they can actually make and control intense beams of this incredibly radioactive and exotic molecule. Text 8 upper Sev 81, that was a huge engineering hurdle they've now cleared.
Second, the quantum key. They found it. They located that critical electronic transition, the readout switch, at 387 nanometers, which makes all future precision experiments possible and efficient.
And third, and most important, the universe's new microscope. The theory and experimental work all confirm that Text 8CF is, right now, our single most promising tool for finding new sources of CP violation. It could improve our search by 3 orders of magnitude.
This work really does change the game. It doesn't just suggest a new experiment. It validates a specific molecule as the best path forward to solving why we're all here.
Absolutely. When you step back, the search for CT violation is really the search for the reason we exist. It's the hunt for that missing puzzle piece that explains why matter survived the Big Bang. And this research puts a powerful new tool right at the forefront of that hunt.
Which leaves us with a final thought for you to chew on. This Text AC molecule is what's known as a closed shell system. It gives us different complementary information to open shell molecules like thorium oxide that have been used in other big searches.
A very important distinction.
So the question is, given that new physics could be hiding in many different places, what combination of all these different quantum detectives, the closed shell ones, the open shell ones, and maybe others we haven't even found yet, might be the key to finally unlocking the complete map of CP violation and solving this cosmic mystery once and for all?
A fascinating question for the future of physics. Thanks for joining us in the lab for this deep dive.
Subscribe to The Deep Dive for your shortcut to being well informed. We'll see you next time.